Hi everyone. Let's now look at the last part of this chapter, which is a graph neural network. So far, the methods that we have discussed, right? For example, node to wake, deep work kind of methods, where we look at random work for embedding. We also have looked at matrix factorization based approaches. So all these approaches are kind of statistical approaches in the sense like uh, it basically tries to minimize or maximize some objective function without considering explicit neural network structure as such, right? So now what we will discuss today is graph neural network, where we will see how we can incorporate the vast amount of neural network architecture that have been proposed so far for different other domains like computer vision, speech, right, those domains, and how we can incorporate those for graph processing, right, graph embedding. So neural network, deep learning, we all know the impact of deep learning in today's world. I would say post 2010 2011, right, era, we have seen multiple such cases where deep learning based approaches just outperformed statistical approaches in most of the domains. And graph domain is also one such domain where deep learning completely overshoots most of the traditional methods. I am not going into the details of deep learning. The TA of this course, Shivani, has already talked about deep learning, the foundation of deep learning in the previous lectures. I think she has already talked about normal neural network, feed forward network, RNN, CNN, attention, this kind of methods. Hope you have fair bit of ideas about this. I am assuming that you guys are aware of all these techniques, at least briefly. So I will try to explain graph neural network again in a very abstract manner. I will not go into the details of every bit of this, because if I go into the details of every bit of this part, this would take another course separately, because the way this particular domain is evolving, right, after 2017 2018 years. So after that, people have seen plenty of methods where this kind of neural networks have been incorporated for graph processing. Okay, so so what is the fundamental ideas behind what's the fundamental idea behind graph neural network? You basically have an image, right, and let's assume that you have an image, right, and for image domain, how we generally extract information, extract features, we essentially use some sort of convolution operation. We have fixed grid, and that grid moves over the image, right, and you basically get a condensed representation of every grid, right, from every grid, and then and then you basically squeeze the representation, and you keep on squeezing it, and finally you get some sort of application, right. You feed that representation to the application. So now one may wonder that let's use GCN, let's use convolutional operation on graphs, right. But the problem in graphs is that unlike image, right, which basically uses a RGB kind of matrices for representation, or speech, which is basically sequential in nature, right, where you can quite easily do convolutional operation, because you have a fixed structure, and if you manipulate, if you modify the grid, for example, if you modify the sequence, you get a separate representation altogether, right. So your image will change altogether, the speech sequence will change altogether. But in our case, when you have an adjacency matrix, and if you swap rows and columns, we discussed earlier, if you swap rows and columns, we basically rename nodes, right. So the network structure will remain same but the adjacency matrix will become now different, right. Now on a different matrix, if you do the same operation, you may you expect that you get different output, but the graph structure remains same, right. So you should not get different output. So that's the major concern here. That's why traditionally the way we you know use convolutional operation doesn't work in case of graphs, right. So, so the rest of the part that we are going to discuss today, that part is highly motivated by Uriel Escobic's course on machine learning for graphs, as well as the beautiful the book, right, on deep learning on graphs, right, by Jillian Tang. Okay. So, if you are interested, you can also look at this book and the lecture series. You get fair bit of ideas about graph learning using neural network. So, in case of graph, right, how do we think of a convolution operation? Okay. So, let us draw a picture here. So, let us assume that right. So, what a convolutional operation does, if you think of it carefully, you have an image, right. Let's think of it in case of image, and you have this matrix, right. Now, you have a kernel which keeps on moving, right, and from each particular region, right, you get a representation, right. What you basically do, you do some convolution operation, and you get a condensed representation of this part here, right. So, let us say you have you have an 8 cross 8 matrix here. From 8 cross 8 matrix, you possibly get a, say, a 2 cross 2 matrix, right. Now, the good part about image is that, as I mentioned, is that the reference point here is very clear. For example, when you think of this region, right, you know that the central point is this one. This is the center point, and with respect to the center point, you can think of a 2 by 2 2 cross 2 region, right. But think of a graph, right. In case of graph, how do you decide the central point? What do you mean by a central point, right? And another point, and another interesting feature in case of image, is that that this kernel, right, the dimension is always same, right, and it focuses on a 2 cross 2 region, right, and that region is very that region is fixed, right. But in case of graph, so let us say you think of this as a central point, you can think of this as a central point. Now, you can you can think of this as a region, one of say EgoNet, right, as a region. You can also think of, now if you assume this as a central node, you have 1 2 3 4 neighbors. What about this one? If you consider this as a central point, then you have this as a region, right, where you have 2 nodes, right, you have 2 nodes in this case as neighbors in this region, but here you have 4 nodes, right, as neighbors in the region. Now, the region is not same. What I mean to say, in case of graphs, the region is not same. So, how can we tactfully use convolution operation here in case of graph? We will discuss this, but another point to ponder is that we also want that the topological structure as well as the feature of nodes would also be preserved, would also be considered while doing neural network, while running neural network, right. So, right, so I mean, one can think of a normal, say, feed forward network where you have, say, a 2-layer network, right, like this, a 2-layer network, and you can say that, okay, let us think of the adjacency matrix here, and say 1 2 3 4 n 1 2 3 4 n. You have rows indicating neighbors. You can also add additional rows indicating features, right, for each node, and then you have a concatenated version of feature vector, right. This part indicates neighbors and this part indicates features, right. And you can say that okay, what I can do, I can just feed this, right, in the neural network and let the neural network produce some representation. Similarly, you feed this to the neural network and let it produce something, and so on and so forth, right. But this is a terrible idea. Why this is a terrible idea? The reason is that first of all, let us say you have a graph of 100 nodes, right. So, you have a neural network of 100 dimension, right. Now, let us say you want to use the same neural network for another graph, right, of size 50. Now, how can you use this one? You can't use it because you have now 1000 or 100 nodes whatever, right. How can you fill the remaining part here? This is one problem, and the second problem I already mentioned. This should be order variant, but here this is order invariant, right. If you change the order, what would happen is that if you swap nodes and columns tactfully, you may, you will end up getting the same graph, but the neural network won't be able to understand whether this is same graph or different graph. Okay. So, how do we tackle this problem? So, in case of graph, right, GCN, okay, graph convolutional network. So, in a normal convolution operation, the CNN kind of tool when we use, what are the two basic operations that we do? So, one is the aggregation. So, we basically fix a particular region, put a kernel, aggregate information from that region, and then non-linearity, right. That aggregated information is passed through a non-linearity and it produces something. So, here also we will do the same thing in case of graphs, right, but in a different manner. So, what we do here, the neural network that we create, right, would be would basically driven by the topological structure of the graph. Okay. Let us say you have a graph like this, okay, say A, B, C, D, E, F. For every node, we will first create something called computational graph. Computational graph. Okay. Now, remember this computational graph would be different for different nodes. Okay. Let us say we fix that the depth of the computational graph would be 2, right. So, we will not move beyond second half, right. Now, for node A, so node A will basically receive information from B and C, right. If you look at right, its immediate neighbor. So, this is A, B and C. If you look at B is one of neighbors, right, would be A and C. C is one of neighbors would be A, D, E and B. Okay. So, this is the 2 hop or 2 label computational graph for A, right. Now, remember what we do here, there is something called message passing setting, right, message passing. So, in a normal message passing setting, what we do, we basically pass messages from the neighbors to the original node. So, say you have V and V's neighbors. So, first you basically pass messages from V's neighbors to V. Now, V will then further pass that message to its neighbors and so on and so forth, right. Similarly, here we use the same idea. So, message passing paradigm would be used for graph convolutional network. Now, so this is the computational graph for A, but the computational graph for, let us say, F, right, would be different. For F it would be E, then F, D, C. This is more skewed, right. Similarly, the computational graph for C, B, D, other nodes would be different. Now, what we do once we create this computational graph, right, we will basically add a convolutional block, right, here at every junction, here, 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 okay, in this case here and here. So, these are convolutional blocks, right. What it does, each of these convolutional blocks, what it does, it basically takes inputs from the corresponding nodes and aggregate it, right, pass it to some non-linearity and then generate the output, and the output will be passed to the next layer, right. So, this is the idea, but remember this computational graph would be different from different nodes, right. Therefore, I said that the neural network that we design. So, this is a neural network of depth 2, neural network of depth 2. Now, k equals to 2, this depth is an hyperparameter that we need to set, okay. And now let us look at individual region, right. Let us look at each of these blocks, right, what it does, right. So, it basically does the following. So, let us say this one, right. So, it basically aggregates information, messages passing from A and C, coming from A and C. It first aggregates, right, and then it basically passes it through passes this aggregated information through some weights, again some neural network. You can think of it as a one depth 1 neural network, and it also aggregates its own information. So, every node has some message at particular time, at particular iteration, right. Let us say at k equals to 2, this node has a message, this node has a message, this node also has a message, right, this node also has a message. So, the updated message at k equals to 3 in this node would be a function of these two nodes messages and the message that is there in this node, okay. So, let me write what I exactly meant to say. Now, this message is nothing but representation, right. So, at every step your representation is getting updated, right. So, representation denoted by H of a particular node V at a time k, right, would look like this. So, you have some aggregation function. Let us assume that the aggregation function is simple mean, right. So, it would be summation of the representation, right, all V's neighbors, right. V's neighbors are A and C. So, U, which is a neighbor of V, right, U k minus 1, right, and how many such neighbors are there. So, right, this would be the mean, right. So, this is the mean aggregation, right, of V's neighbors, right, and you basically have a parameter Wk with this, and you have another information coming from this node, which is H V k minus 1, right. This would also be parameterized Bk. Now, what is this? This is the message of this particular node at k minus 1th time, and you are planning to get the message for V at kth time, Okay. So, this is the aggregation. Okay. These are the two parameters that you learn. These are basically neural network parameters, and then you pass it through a nonlinearity, sigmoid kind of nonlinearity, right. So, at every block, at every such box, it basically takes its neighbors, aggregates, and then it is parameterized. Similarly, you have your own message parameterized, aggregate them, pass it through nonlinearity and get the output. Okay. So, this happens at every stage. Okay. So, this W and B, right, these are the parameters that we need to learn. Okay. Think about it. So, think about it. Now, this W and B, right, it also depends on the depth k, time k. If there are two depths, so you will have W1 B1 for this depth and W2 B2 for this depth, right, and these are trainable parameters. Remember, these parameters W and B, these parameters are shared across nodes. These parameters are shared across nodes. Wk, the value of Wk Bk, the same value would be here and here, because the dimension is same. Remember, ultimately you are aggregating. So, the dimension would be the dimension of the original message D after aggregation. It is not concatenation, aggregation. So, the dimension will remain same. Okay. So, this is the idea. Now, a few points to mention here. This is the hyperparameter that we set. Generally, it is set to 2. It can be 3 also, but not very I mean very high, because if you keep it, if you make it very high, then you exhaust with all the nodes, right, with the entire graph, which we do not want. Secondly, this aggregation operation, right, this should be order invariant, in the sense like if I make this as C and this as A, the aggregated output will remain same, right. It should not be dependent on the order. Sum is an order invariant aggregation function. Mean is also an order invariant, right. Mean, max, these are all order invariant operations, right. So, you can use all sorts of aggregation operation for I mean for here, for this part, right. You may also wonder, why do we need these two separate parameters? Why are you not just adding this part here and dividing it by NB plus 1, right? This can also be done, but remember, the impact of my neighbors should always be different from impact of my own message, right. I want to keep these two things separate. I always, sometimes I want that my own message would be of more importance than my neighbor's message, right. Therefore, I would want to give more weightage here and less weightage here, right. So, now how do you initialize this neural network? So, I mean, how do we initialize these messages? What do you mean by message here? Message is basically, I mean, if you have a feature, right, node feature, you can initialize. So, this H is basically hidden state, right. What would be H V at 0 at the initial stage? It would just be the feature of node V, right. So, you are basically passing the features from one hop to another hop, right, and this is the idea. And if you don't have features, then you can just use some sort of node level information like degree or clustering coefficient. These information can also be used as a proxy of features, right, or you just set everything as 1, right, and you basically pass it and let the neural network decide, because ultimately it also depends on the topology, right. So, and how do we train this model? There are two ways to train this model. First way is a simple unsupervised way. For example, node to wake, deep work type ways we can train the model. The second approach is more of a supervised approach. Let us say the task is node classification, right. So, after this layer you can think of a classification layer, right, which will say whether it is say fraud or genuine or whatever, red and blue, right, and you have the loss function, right. You basically take the derivative of this loss function and back propagate it, right, and you update the representation. Okay. So, this is the idea, and this is vanilla GCN. On top of this you can also add additional constraints like the relations, right, and so on and so forth, and depending on that methods like ArcGCN, all these methods have been proposed in many literature, and you can also look at those things, right. For example, ArcGCN you can also consider edge types, the relations, right, particularly for knowledge graphs, right, and you can have embeddings. I mean, you can think of this neighbor as not a raw neighbor, but neighbors are now dependent on the relations, right, and you can have this learnable parameters which would be a function of the relation R, right, and so on and so forth. So, in the next lecture we will discuss two other methods, which is graph sage and another would be graph attention network. Thank you.